Good evening, everyone. Welcome to the problem solving section. Um, Today, it's a summary section for course Digital Electronic Circuits. So, we will solve some topics, uh, like solve one questions from each topics. And to begin, let's start with the number system. We will parallelly discuss, revise some of the concepts and solve one questions. So, let's begin. The number system. First, let's convert a binary number to decimal number. So, let's take an example. If this is a binary number, then to convert this to decimal, we will multiply. This is, I'm writing the place value. So, it is 2 to the power 0 plus 2 to the power 3 plus 2 to the power 4. It is 1 plus 8 plus 16, and which is 25. So, if you want to convert any number from binary or any number system to decimal, we will multiply with the place value. So for that, let's convert an hexadecimal number to a decimal number. So if hexadecimal number, if you take 1f, which is say in hexadecimal, then again we have to take the place value. So f into 16 to the power 0, which is 1, plus 1 into 16 to the power 1. So it is f plus 16, which is nothing but 16 plus 16, because f is 15, and this is 31 in decimal number system. So similarly, if you want to convert octal to decimal also, each place value you have to multiply. So this is a procedure for converting from any number system to the decimal number system. Now let's see a procedure to convert from decimal to any other number system. So for example, let's consider hexadecimal. Then I'm taking 31, which is in decimal. Now, if I want to convert that to hexadecimal, I have to perform division, long division. So, with 16 for hexa, it is octal by 8 for decimal, binary 1, 2. So, this is 16 into 1, which is 16, and 15 is the remainder. So, we write in this order. So, it is 1f, and this is in hexadecimal. So, now, show one more example. For converting decimal number system to binary number system. Now let's convert a decimal to binary. Let's take the example of 25, which is in decimal. So 25 for decimal, divide by 2. And it is 12. So 1, 2, 6, 0, 2, 3, 0, 2, 1, 1. Again, write in this order. It is 1, 1, 0, 0, 1 in this. This is in binary based number system. In this way, you can see with this place value, we multiply from converting to any number base number system to decimal, and from decimal to any other number system, we are performing this division by the base, like binary divide by 2. For hexa, divide by 16. For octal, it will be divide by 8. Okay. With this, now let's take some more example. Let's convert a binary to octal. And for this, we have to have a group of 3, because octal is 0 to 7, So we need 3 bits. So it should be a group of 3. And let's consider it is, this is the example. Then how we will convert? Group of 3, group of 3, group of 3. And from here, this group of 3. If this 0 is not there, we have to add this 0. So this is 4, 7, 2.2. This is the octal number. In the same way, if you want to, and vice versa, if we have this number, then each number we have to write as a group of 3. Two is 0, 1, 0. Point two is 0, 1, 0. We have to, while writing again, 3 bits each. So in this way, you can convert octal to this binary back. So next, if we have an hexa number to binary, and here this is a group of 4. Why 4? Because hexadecimal number system ranges from 0 to 15, which is 0 to F, and we need 4 bits to represent each digit. So in the same way, if we consider an example, like if you want to convert 9F to 16, which is a 16 base 16, to binaries. So 9 we can represent as 1, 0, 0, 1. F represent as 4, 1. 2 we have to write in group of 4. So in this way we convert to the decimal. Same way, when writing back, we have to group from this place, group of 4, group of 4, starting from this right hand side, group of 4, group of 4. So this is 9F and 2. Okay, so with this, we will go for another question. A typical CD-ROM can store 650 megabytes of digital data. Since megabyte is 2 to the power 20. Is the voice clear now? Is it fine now? Okay. A typical CD-ROM can store 650 megabytes of digital data. Since mega is 2 to the power 20, how many bits of data can a CD-ROM hold? So they have, it is given that it has 650 megabytes. So 650 megabyte means 2 to the power 20 into 1 byte is 8 bits. So it can hold 6, 5, 4, 5 to 595, 200, this many bits. Okay. Next, we have another type of numbers called as BCD numbers, which is binary coded decimal number. So we have from 0 to 9. So in it is represented as a group of 4 from 00004 zeros to 1001. This is the BCD numbers. Now, for example, I have in decimal, say 874, and I want to convert this to BCD. Each digit I will represent with 4 digits, 4 bits. So anyway, in decimal it is from 0 to 9. So each digit with 4 bits. 8 can be represented as 1000, 7 can be represented as 011, and 4 can be represented as 0100. So this is the BCD representation. I hope the voice is clear now. So next we will take this. It is in decimal. Now to convert to binary, so we have to perform long division. Okay. So if we convert, it is equivalent to this in the binary. But whereas in the BCD, each digit group of 4. So 0001 for 1, 30011 for 70111. So this is the representation in the BCD number system. Um, it's 68 with 1, 34 with 0, 2, 1, 7 with 0, with 16. So 8 with 1, 2, 4s are 0, 2 2s are 0, 2 1s are 0. So in this way you have to write, and this is 130100 in the binary for 130. So this, I hope you understood how to convert a number, decimal number to binary, and decimal to any number system, any number system to decimal, and what is the BCD representation, and how to convert a decimal to BCD, and how the number looks different in both decimal and BCD. Okay, so with this, we will go for some questions. So I will give you the circuit, find the Boolean expression of at the output. If this is the Boolean circuit given to us, and let's represent this as x, then what is the expression for x? So here we will have a bar. I will use some other colors. Here we will have a bar. Here we will have b bar. And what is the output of our gate? A bar plus b bar. And not get a bar plus b bar whole bar. It is a and b. And this is b. And this is c. So x is a, b, c. So going to the next question. In the similar way, let's have another Boolean, another gate level logic diagram. C, B, A. And what is the expression of x? Here, this output will be NAND gates A, B, the whole bar, and this output will be C bar plus B whole bar, and final output A, one term is A plus B complement, and with B plus C bar whole complement and another complement. Now, if we apply Boolean algebra, De Morgan's theorem, we can simplify as we have to break this bar at here and change this sign. So it will be plus, and this will be A1 B. Sorry, this is B plus C bar bar. So this is equivalent to A plus B plus C bar. 2 times B is equivalent to 1. Yes. B plus B is B. So now when x is 0, x is 0 only when A is 0, B is 0, and C is 1. If either of them is 1, then it will be 1. So it is that. Like 0, 1, say 0, which is output is 1. So for this to be 1, for x to be 0, so this is if it makes sense. For x to be 0, only when A is equal to 0 and B is 0 and C is 1. Okay. So next we will solve some questions simplifying using the De Morgan's theorem and some other and also other Boolean theorems. So simplify using De Morgan's theorem. So the question is A bar, B, C bar, full bar. And the next simplification is A, B, C, B, and the third simplification. So this A, B plus C bar D. This complement this. So can you please try parallelly with me? This I break the bar, this changing the sign, then this will have complement. This the complement's complement is the number itself. So A plus B bar plus, for this A bar plus B bar plus, here let's keep the same thing so that we'll have A bar plus B bar plus C. And for this A bar plus, take this bar, then this bar is this complement will go. So it is B plus C bar, and for this again plus D complement. So this was some of the simplification or using the De Morgan's theorem. Next, we will implement y is equal to A, B, C, D using only two input NAND gates. So, and how many NAND gates are required? Let's first do A, B. This is first. So it is A dot B NAND operation. If we apply to another NAND gate, we will have A, B, A and B. Now we have to apply C to this. So we will have A, B, C whole complement. And again, if we apply this 1 and 8, it will act as an not operation. So the next third. Now this will give A, B, C, D whole component and apply through a NOT gate to get A, B, C. So total 6 NAND gates are required. This is one of the implementation, and this is the YS A, B, and C and D. Next, we will solve some questions on simplification. So let's simplify this Boolean equation. B is equal to A, B, C plus A, B complement and with A complement, C complement equal. And the next simplification, I want to simplify X is equal to A complement plus B, A plus B plus D, D. Let's simplify one by one. C is equal to ABC plus AB complement, A complement, C complement, whole complement. Now, applying the De Morgan's theorem. A is larger. Now is the screen visible? I will go a little slow. Now applying the De Morgan's theorem. A B complement, A complement complement plus C complement complement. So this is A B C plus A B complement A plus C as we can cancel the double inversion. So the next term, if you multiply this A B complement inside, it will be A B C plus A B complement plus A B complement C. Now A into A is A. A and A is A. So A B C plus A B complement plus A B complement C. Now we can take A as a common and C as a common from these two terms. Then B plus B complement plus A B complement. This is AC into 1 plus AB complement. The simplified expression AC plus AB complement. Also you can write as A has common C plus B. The simplification. Now let's simplify our second expression, which is A complement plus B and A plus B, A or B or D and with D complement. X is equal to A complement plus B, multiplying the D inside, taking the D inside, A D complement plus B D complement plus D complement. And you know D complement is 0. So A plus A complement plus B, A D complement plus B D complement. Now multiply A complement A D complement plus A complement B D complement plus A B D complement plus B B D complement. And B complement is B complement. So A complement B complement. This is 0. Plus B complement plus this is B. So B complement. Now in these two terms, D complement is common. So it is A plus D complement plus, and this will be, and this we have already seen, it is equivalent to any doubts still here? Next we will see K-map. K-map means Karna map, and it is used for simplifying the Boolean equations. So we have something called as looping. We perform to minimize it, and it is called the process of for combining the ones or zeros. So now let's take example. A, B, C. So here it is 0, 0. So C bar D bar. 0, 1, C bar D. 1, 1, C D. 1, 0. So C D bar. The same way here also. Say consider this are the bits which are 1. And let other elements be 0. So one of the possible combinations to form group of 2 or pair is this can form one pair, this can form one pair, and this can form another pair. There can be other possibilities, but I am shy of one for example to show that you can form groups from this like this or horizontally, and also inside in the Karnama horizontally as well as vertically. So how to write it? First, if we take this expression, it is A bar B bar is not changing and C is not changing. Let's, we want to write for this. This is forming here. So A B bar is not changing. And what is not, D bar is not changing, plus your third expression for this, C bar D is not changing, and here B bar is not changing. In this way, we can form a group of two elements. Next we have is we can also form a group of 4 and group of 8. And when forming the group, we will search for the highest possible group. We'll start if 16, whole 16 is possible or 4 is possible. 16, 8, 4, then 2. Otherwise, we will form a group of 1. And this is for the 4 variable K map. If we consider this entries in the K map to be 1 and other entries to be 0 to show the possible one of the possible group, and group of 4 is called a squad. So will be this 4 can form one group and the other group can be formed by this 4. So X is equal to, for this group, it is A and D bar. You can see as the number of group increases, like when we had a group of 2, there were 3 variables instead of 4. And when we are forming a group of 4, we are having 2 variables. Plus, now this. Here, B bar is not changing and D bar is not changing. Next, and this is this here CD instead of CD bar. It is due to the gray coding, and gray coding, every number, successive number has a 1 bit change. So if we consider this to be 1, then to form a group of 8, we can have like this, and also similarly the both horizontal and vertical direction. So here you will see that it is having just one variable. So this one, this complete is changing, only D bar is not changing. Plus this one, only B bar is not changing. This is all about the K-map. Next, we will see, we will use the K-map in solving this question. So a 4-bit binary number is represented as A3, A2, A1, A0, where A3, A2, A1 and A0 represented individual bits, and A0 is equal to the LSB bit. Design a logic circuit that will produce high output whenever the binary number is greater than 0010 and less than 1000. This A3, A2, A1, A0. A0 is the LSB bit and the I am writing the truth table for the implementing the function given in the question. Yes. Can you tell me what will be the truth table when the output will be 1? So it is given that output is 1 when greater than 0010, not greater than or equal to. So it is greater than and less than 1000. So from here till this, when it is 8, it is back to 0. Now to simplify this, we need K-map. A3, A2, A1, A0. Here also you can directly fill, you will, as you know, this correspond to 0, 1, 2, 3, 4 in decimal, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. And you know this is 2 and this is 8. So 1 should be filled greater than 2, 1, 3, 4, 5, 6, 7 and 8 is 0. So how can we simplify or group this? We have one quad and one pair. So excess A3 complement A2 plus A3 complement A1 A0. So we can take A3 complement as common. So we get A2 plus A1 A0. Okay. So next we have synchronous and asynchronous input. What is a synchronous input means that the inputs that are affected or changes with synchronous to the clock. With the synchronized to the clock. And whereas asynchronous synchronous asynchronous input means that inputs that operate independently of the synchronous input or the clock. Synchronous input and the clock. So the synchronous inputs are the inputs which are going to change the output or are getting like are the output with synchronized to the clock input, and the asynchronous the inputs that operate independently of the synchronous input or the clock. Okay, so these are some definitions I just wanted to share. And next is the setup time, hold time, and propagation delay. If we consider that this is the input of the circuit, say this is the control input from this 50%, if this is the clock input, then this duration is Ts, and this is synchronized input. This changes with respect to the clock. So this time is called the setup time. A data input should be held for a certain amount of time before the application of the clock or before the clock edge is known as the setup time. And in a similar way, I'm writing here, if this is the data and this is the clock, the time duration, this TH, is called as hold time. The time duration we should hold the data input stable after the application of the time, after the application of the clock is called as the hold time. And next we have propagation delays. If I have a clock with this is okay. Now propagation delay. So I have a clock and say the output Q. This 50%, it will take some delay and then reflected at the output. So it's 50%. This 50% to this 50% is called as the propagation delay, and it's a low to high. So TPLH, propagation delay low to high. The same way, actually this is input and this is clock here, and here it is clock and the output. So this clock is rising and this 50% delay we want, and the output is say discharging. If this is the Q, this 50% is known as the propagation delay TP, and it's high to low, so HL. And again this is the 50% and this is the 50%. Okay, so next we will solve some questions. Assume that mod 8 counter is in 101 states. What will be the state count after 13 pulses have been applied? And if you consider this as an up counter, can you please repeat? Which one you want me to repeat? You can unmute yourself and also speak. If setup time. Setup time is that this is the input. The time input should be stable before this clock edge. If a flip flop is operating at the positive edge, this is the rising edge. Before this clock edge, this input should be stable for a certain amount of time, and that is called a setup time. And after the application of time, again the input data should be kept stable for a certain amount of time, and that is called as hold time. Is it clear for you now? Is it clear? Okay. So you know what is the state diagram for model? It is, if it is given as up counter, so it will count 0, 1, 2, 3, 4, 5, 6, 7, and 8. So 0 to 7. It's a 3 bit. So now it is in this state. So they said they have given 13 pulses. So this will be the first pulse. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it will be in this state. Okay. So let's solve this. In the fifth, it will be in state 5 initially. This is 5. Then go to state 6 in the first clock, plus 7 in the second clock, plus another 0 to 7. It will take 8 clocks. How much clock we are having? 3 more clocks. So 0, 1, 2. So this will be 1, this will be 1, this will be 1. So it's 8, 9, 10, 11, 12, 13. Then this is 10. This is another clock. Right? So 10, and this is 13 pulses. So it is in the state of 0, 1, 0. So the next, consider counter circuit that contains 6 flip-flop wire to form up counter. So what will be the modulus of the counter? Modulus of the counter is 2 to the power 6, which is 64. So it's a mod 64 counter. And determine the frequency at the output of the last flip-flop Q5, which when input clock frequency is 1 megahertz. So F at Q5 is 1 megahertz divided by mod of the counter, which is 64. This will be around 15.625 kilohertz. What is the range of the counting? It is from 0 to 63 in decimal, or it's 0, 6 flip flops. So 6 zeros to 6 1. This is in decimal and this is in decimal binary. Okay. decimal system and binary system. Okay. So next we will see noise margin. Noise margin, to start with, we have, let's consider this to be the output, 0, L is equal to 0, and high, which is logic 1. So this point we call as VOH, output high, output low, VOL. And this is the region in between. And this is in volt. A similar way, for the input, this is here. Look at this marked here. This region and this point we call as VIH, input high and input low. Now what is the noise margin? We have noise margin high and noise margin low. So this is called as noise margin high, and this difference is known as noise margin low. How much high can an input be? Still it is deducted as a low, and whereas how much low an input voltage is, because that is deducted as a high. Okay, so this much low you can go, but still it will be logic high, and this much high you can go, but still it is logic low. And this distance is known as the TW, which is the transition width. So the noise margin low is the difference between VIL minus VOL. VIL minus VOL. And the noise margin high is VOH, this region, to this V minus VIH. And this transition width, this is called as transition width, is VIH minus VIL. And with this we have the range. You can see VOH is the minimum value, and which is the greater than VIH, which is also the minimum point, which is greater than VIL, which is the maximum point, and which is greater than VOL, which is the maximum. And then we have something called as overall noise margin. The overall noise margin is the minimum of noise margin low and the noise margin high. So this is about the noise margin. And next we will see the dynamic power. Dynamic power. So the dynamic power, there are two types of power. One, which is the power which is dissipated when there is no operation or no activity, which is static power, like not like activity, without any function. The circuit is idle, but still due to leakage there is a power, that is known as static power. And dynamic power, when the circuit is operating, and the dynamic power is given as alpha CL VDD square into F. And static power is the leakage, so leakage current into the voltage. And this alpha is the activity factor. How to calculate this activity factor? So if we consider alpha to be 0 to 1 transitions, and it's the probability the number is 0 and 1. So probability is 0, 1 minus it is 1. This is calculated as number of times a 0 is appearing by 2 to the power n and number of times 1 appears by 2 to the power n, which is nothing but which is given as with this formula. So if we consider an inverter when n0 is 1, one time the 0 occurs. So this activity factor is 1 by 4. And similarly for NOR gate, which has 3 inputs and the number of times 0 occurs is 7 from the truth table. So the alpha 0 to 1 transition is 7 by 60. And the implementation is CMOS logic. We need 2 PMOS in the parallel and 2 NMOS series. So this A, B, it is in series. So this gives Y to be A, B, and CMOS logic, so it's giving complementary logic. So A, B complementary. And this input should be A. So this is the NAND gate operation. And to implement the NOR gate, the series hello. So the NOR gate implementation, we have A and B in series in the pull-up network, and in the pull-down network we have A and B in parallel. So this gives A plus B, because any one of the transistor, if it is on, we have a path to ground and it's giving 0, so it's complementary. So these are implementation and how we write the function from CMOS base circuit. So next, consider the following CMOS circuit and identify the output. So I will give you the circuit. And we have a pull-up network. Now to design the pull-down network, you could have seen that A, B are in parallel. So here A, B should be in series. And C and A are in series. In the pull-down network, C and D should be in parallel. And to this parallel, here it is parallel to E, so it should be in series with input E. Now what will be the expression of V out? This too is A, B, because both are on, then only there is a path to ground, and it's in the complement form, so we will take that complement at last. And here any one is on C or D, it will connect to E, and when E is also on, it will connect to ground. So, and any one of the path is on, either A, B, or C plus D and with E, it will have a path to ground, not the VDE. So it's complement. Is it clear? So, any doubts still here? Okay, next question. Simplify the following expression. F is equal to BC plus BC bar plus BA. Can you try simplifying this? What will be the simplified expression? First, we can take B common, so it will be C plus C complement plus BA, and this is B into 1 plus B into A. Next, B can be taken as complement, so it is 1 plus A, and 1 plus A is 1. So this gives B. So F is equal to B. So next, product of sum, which is POS, and it is the product of max terms. So how we represent if we have say A, B, C, and example if it is A, B plus C bar, A bar plus B plus C, A bar plus B bar plus C bar. Then we represent this with the notation pi because it's product term and capital M. So, and it is the product of max terms. So what is the max term? This is, it is 0, 0, 1, 1, 0, 0, 1, 1, 1. So it's a product of M1 and with M4 and with M7. Also denoted as pi of M 1, 4, 7. In the similar way, if we have an SOP term, say f of A, comma B, comma C is equal to so this is equal to 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1. And this can be written as sum of product, which is the sum of the min terms. There it was the max term. These are the max term. And here we have is the min term. So we can write M0 plus M1 plus M4 plus M. And here it is denoted as summation of M014. Okay. Next, we will see canonical. If we have f of A, comma B, comma C is equal to AB plus B complement, A complement plus C complement. Then we have to multiply this B complement inside, so we get A complement B complement plus B complement C complement. Now to get the minterms, canonical forms. Each minterm should have all the terms. So it's a three variable function A, B, C. So each term should have A, B, and C. So this could have been obtained by simplifying C plus C complement. And again, this could have been obtained. This is individual complement by simplifying C plus C complement to be 1, and this by A plus A complement. Now you have to multiply this inside. So it is A B C plus A B C bar plus A bar C B bar C plus A bar B bar C bar plus A B bar C plus A bar B bar C, which is nothing but summation on 0, 1, 4, 6, 7. In this, if we have a K map, we can easily write this expression as A. It's a three variable K map. A, B, C, 0, 1. Now it is given A, B. So A is 1 in this whole row and B is 1 in this two row. Next is A bar, B bar. A is 0, B is also 0. So A is 0, B is 0. A is 0, B is 0. Next is B is 0, C is also 0. And the rest of the terms are 0. So it is 0, 1, 2, 3, 4, 5, 6, 7. So you can see 0, 1, 4, 6, and 7. So in this way also we can find this canonical form. Next, to convert an SOP to POS form. If we have an SOP midterms as 0, 1, 4, 6, 7, then what will be the POS for this? The POS will be summation capital M2, 3, and 5. The terms which are not included in the SOP. So what is POS? 3 and C, the zeros 2, 3, 5. So it's 2, 3. Okay, next is, let's see, static hazards. We have hazards which can be static as well as dynamic. So let's start with the static one hazard. So any combinational circuit which can be reduced under any particular input combinations to A plus A bar, this is 1. Okay, so this gives a static one hazard. So static one hazard output should remain at logic high, static at 1 to the Boolean logic, but glitch occurs under certain condition. It goes momentarily to 0. Because of this delay. And we have static 0 hazard where for any input combination. So the previous one is static 1 hazard. Output should remain at logic 1, that is static at 1 according to the Boolean logic, but glitch occurs under certain conditions, certain input combinations. For static 0 under certain input combination, the circuit is reduced to this form where Y is equivalent to A bar, then static 0 hazard occurs. So the static 0 hazard output should remain at 0 according to the Boolean logic, but glitch occurs and goes momentarily to 1 and this is under the certain input condition. For the dynamic hazard, the number of levels should be greater than or equal to, and for a specific input combination of the input, the expression is reduced to A plus A bar into A, or A plus A bar. Then the dynamic hazard will occur. So next, so how can we remove a static one hazard? And this is the example I have taken from our previous lecture, where you can see it goes to zero for a short duration of time, where it should have remainder in 1. And how can we remove it? By adding a term BC, which is common to both the terms, so that we have a third path. When there is a glitch, this third path will compensate it. So this is a hazard-free circuit. So the next, multiplexer. So if we have say 2 to 1 multiplexer, then 0, 1, what will be the equation? D0, D1, Y, and the select line will be S0. Y will be S is 0, then it will select D0. If S is 1, it will select D1. So it is a 2 to 1 multiplexer. Next, consider a 4 to 1 multiplexer with two select lines A1 and S0. There is a mirror. It is S1 and S0. The minimal SOP form of the Boolean expression for the F of the multiplexer is, and if you consider the multiplexer given in the question, it's 4 to 1 multiplexer. So 0, 1, 2, 3, and two select lines S1, S0. So let it be PQ and output as 8 o'clock class in the class. And if it is given 0, 1, R complement, then what is the minimal SOP expression for this? So it is P complement Q complement, it will select 0, plus P Q complement, it will select 1. No, it is 1, 0, 1. So P Q complement, P complement Q, plus P Q complement, it will select R, plus P Q, it will select R. Now how to simplify this? Okay. P Q R. So this will be 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Now this is 0. P bar Q. P bar Q should be 1, and Q is 1 in this 2. Is it correct? P bar Q. Q is, sorry, Q should be 1. Q is 1 here only. Okay, Q is 0 here. And next is P bar P Q 1, 0, 1. 1, 0, 1. Next is 1, 1, 0. 1, 1, 0. Now simplify it. F is P Q bar, P bar Q plus Q R plus P Q bar R. This can we simplify directly without the K map? Q, Q, K. This is one method to simplify. This is the expression of S. With this, next we will see Shannon's expansion theorem. With the Shannon expansion theorem, if I expand for one variable, considering n variables x1 to xn, expanding through one variable, we will have f of first 0 xn plus x1 f of 1 x2 x3 xn. So now we are asked what's the question? Implement the function using 4x1 multiplexer and a few other gates as possible. So if the function given to us is a 4 variable function f of w1, w2, w3, w4 is equivalent to, if this is the expression, how to implement this using the multiplexer. So the f, if we expand through Shannon expansion for, you can see W1 and W4 are almost repeating in all the maximum expressions. So I am taking that expanding with respect to W1 and W4. So it will be f of 0, W2, W3, 0 plus f of 0, 1. Any questions? So now expansion. This values you have to substitute to the f of function, and you have W1, W4. If you substitute that, you will have W2 complement W5 plus, so if the number of expression like terms are more, you can see in the expression we have 5 terms. Okay, it's not the function of till W4, it's function till W5. It's function till W5, so here also you have W5. And now we are substituting the 0 and 1 or the values in the bracket to the function and obtaining the expression. Anything added with or with 1 is 1. So the expression we have with us is now you can see this is simplified to the form of a mux with select line W1 and W4, and the inputs we have to apply through sum. generate through some small logic gates. So how this will be? W2, W5. So this is W5, and we have W3, W5. So W5, W3, and next is W2 plus W3, and this is one, and this is our F. What are the select lines? W1, W1. In this way, we can implement any logic expression using the multiplexer, given multiplexer, and using the Shannon expansion theorem. If you want to implement a smaller function, let's consider f is equal to w1 3 complement plus w1 w2 plus using 2 into 2 to 1 multiplexer. So f is expanding with respect to w1 or taking one variable because only one is different. So substituting the values to the expression given, 0 for w1, 1 for the w1, we obtain this expression. So now our select line is w1, output f. When it is 0, it is w3 complement. When it is 1, it is selecting w2 or with w3. Set clear? Next, how can we implement 4 to 1 multiplexer using a 2 to 1 multiplexer? So higher multiplexers, order multiplexer using a lower order multiplexer. So what is the expression for 4 to 1 multiplexer? It is S1, S0 complement D0. S1 complement S0 B1 plus S1 S0 plus S1 S0 D3. So this is, if I take S1 as common, it is S0 D0 plus S0 D1 plus S1 S0 D2 plus S0 D3. So if we can, this is in the form of a 2:1 multiplexer, so we obtain as the output. And again, this is a 2:1 multiplexer. So this final output is also in the form of a 2:1 multiplexer. So if I have a 2:1 multiplexer generating F0, so what it needs as a select line for S0? S0 is a select line. And what are the inputs? D0, D1, and the second multiplexer, which is generating F1, having the select line S1, inputs D2, D3. So this is a 2 to 1 multi-mux. This is another 2 to 1 mux. We have a third 2 to 1 mux, which will generate the final output. And the select line is S1. And what are the inputs? F0 and F1. So in this way, we can convert a design a higher order multiplexer using lower order multiplexer. And also the question is how many such multiplexers are required to generate, like 4 to 1 using 2 to 1, so we have to multiply 2 to 1, 4 is the required one, so we have to. Then next is 2 by 2, we need one more multiplexer, so first stage has 2, second stage has 1, so total 3 marks. So in this way you can calculate the number of multiplexers required. So next is the demultiplexer. If we consider small demultiplexer, 1 to 2 demultiplexer, it has a select line S0 and D is the input. The Y0 is S0 complementary and the Y1 is S0. So the next question. In the following truth table, V is equal to 1 if and only if the input is valid. What is the function does the truth table implement? You can see when the valid is valid, it is encoding this as 0, encoding this as 001, encoding this as 01, which is 1, encoding this as 2, 1, 0, and encoding this as 1, 1. And if it is 0 here, then it is an encoder. But any value at this before, it is taking the priority. So it's a priority encoder. The next question, which of the following is the output AB for the encoder with 4 bits Y1, Y2, Y3, Y4 is equal to 0010. So it's an encoder. So you can see from here 010. It's encoding as 01. One's complement number. So any negative number can be converted to one's complement form by taking the one's complement of the positive number, or which is the inversion of the positive number. And if you see the range for, if we consider an example for 8-bit, the range will be from minus 127 to minus 1, 0, plus 1 to plus 127. And 0 is represented twice. Which is represented as 8-bit, so 8 zeros and 8 ones. So here, if you see, for example, the plus 1 is represented like this, whereas the minus 1 is represented as this. And plus 127 is represented like this, minus 127 is represented in this way. So here we have two representation for a number 0. Next, going to the 2's complement form, we have for every negative number, we take the 1's complement of the positive number and add 1 to it. So if we consider an example of an 8-bit, the range is minus 128 to minus 1, 0, plus 1 to plus 127. And here 0 is represented once. And the representation is So next, going to the 2's complement arithmetic. If we take an example of say 8 minus 16, this can be represented as 8 in decimal plus minus 16 in decimal. So now minus 16, then a positive number is represented as this, taking the 1's complement, which is the inversion, and then 2's complement, which is added with 1. Now we can add this to 8. So what is the value? And here we can see there is no carry. So if no carry, the sign bit is 1. The answer is negative. The number is negative and is a 2's complement form. So now again we have to take the 2's complement. So first 1's complement, then added with 1. So this gives minus 8. We want to try one more example. Let's take an example of 16 minus 8. So again it is 16 plus minus 8. Now minus 8, which is the positive representation is this, taking the 1's complement, inversion. For the binary it is inversion, and then plus 1 for 2's complement. So this is the number. The next 16, which is 301, 0000, and minus 8, which is 1, 2, 3, 4 ones, 1, 000. The answer is 1, 0, 0, 0, 0, 1. We have a carry 0. So if carry exists, then the number is positive. So we have to drop the carry. And what is this? 18 decimal. Previously, we have seen it is minus 18 decimal. Okay. Next, let x1, x0 and y1, y0 be unsigned 2-bit numbers. The function f is equal to 1 if x is greater than 1 and f is 0. Otherwise, f is 0. The minimized SOP expression of f is, it is given x is greater than y, then output is 1. So it is greater expression is g1 plus e1 g0, which is nothing but x1 y1 complement plus x1 complement y1 complement plus x1 y1 x0 y0 complement. That is x1 y1 complement plus x1 x0 y1 y0 plus, this is the expression. Now we have to simplify this expression. And you know how to fill on the expression to the k-map and perform the simplification. the simplified expression we can form. This will be the groups. So the x greater than y x1 y1 bar plus x0 y1 bar y0 bar plus x1 x0 y1 y0 bar. No, y0 bar. Okay, this will be the simplified expression. So next we will see what is the equation g1 g0 E1 are the 1 bit we have already seen. So let's just revise it. So the 1 bit expression for the greater than is x y bar, and for equal to it is an x nor operation. The expression is this, and for the lesser than, this is the expression. And next, if we consider n bit, where the two inputs are xn minus 1, xn minus 2, x1 x0, y yn minus 1, yn minus 2, y1 y0, then the expression for greater than is as given here. And the equal to expression is given as and the lesser than expression can be obtained this simple way. It is these are the expressions. So this is about the magnitude comparator. Modulo of the component decided in one case, one flip-flop in count 0. So it is next. So the truth table of JK flip-flop, if we consider, it is no change, reset, set, toggle. No change, reset, set, and invalid. And for D flip-flop, 0 is 0, 1 is 1. Whatever is the D input is available at the output. And next, toggle flip-flop, Qn plus 1. Toggle is 0, then the output is no change. If toggle is 1, output toggles. And next, if four flip-flops are connected to achieve f by x, where x is the frequency, then what is the maximum value of the x? So it is 2 to the power 4, which is 16. The modulus of the counter is 16, and we achieve a frequency of f by 16. Next, how many minimum number of flip-flops required to make mod 480 counter. 2 to the power 512. So we have this mod. So 2 to the power 9 is 512 and 2 to the power 8 will be less. So we need 9 flip-flops. Okay, the next question. The clock frequency is 24 megahertz is applied to a cascaded counter of mod 4 counter mod 5 followed by mod 6. What are the lowest and the overall modulus respectively? So it is given that we have connected mod 4 followed by mod 5 and followed by mod 6. So the overall modulus of the counter is 4 into 5 into 6, which is 120. And the F out frequency is F divided by the overall modulus, which is 24 mega divided by 120. And this is 0.2, which is 200 kilohertz. Next question. Suppose we want to design a synchronous circuit that possesses a string of zeros and ones. Given a string, it produces another string by replacing the first one. So it sees the first one, it will replace as 0. The next one, it will leave it. So consider this example. And now we have to design using a Mealy machine. Okay. So the Mealy machine, it sees the first 0, it stays in the 0. And other 0, it will stay. First one, it will change to 0. And after that, all one, it has to be 1. Again, if it sees 0, it will go to 0. So we have present state, which is given to be S, denoted as S. Input, denoted as B. The next state, denoted as T. And the output, denoted as Y. If it is 0, input is 0, it remains in 0, output is 0. If it is in 0, output is 1, it goes to 1, but output is 0. If it is in 1 and gets 0, it is in 0, output is 0. If it is 1 and input is 1, so it's 1, 1. This is the next. From this you can see T is equal to the B. And what is Y? This is 1, where S and B are 1. So S and B are 1. So in this way, you can get the expression. So this you can have the table present state input, next state output, and now if you want to implement it, you need the corresponding flip flop J, K, that input value, or D input. Okay. So next question is flip flop conversion. If we want to convert, say, a JK flip flop to D flip flop, so the available flip flop is JK and the required flip flop is D. So we have from the required flip-flop and JK from the available flip-flop. So with this, what will be the next state? It will follow the D. And what will be the JK? We need the excitation table of JK. So filling this will be 0x, 1x, x1, x0. So simplifying using the game up, Qn D for J 0 1 0 1. So it is 0 1 x x. So we can simplify this. J is equal to D. And next Qn D 0 1 0 1 x1 x0. So K is equal to D complement. So in this way, you can convert a flip-flop to any other flip-flop. Next, we will see the BCD addition. The result is valid BCD numbers when the 4-bit sum is less than or equal to 9. So if we have, say, this as an addition number, this gives 0 0 1, which is 9. While adding, we have 1 carry. Or if we have 8 plus 1 is 9. So these are all valid addition. But when the result is not valid, when the 4-bit sum is greater than 9, we have to perform an addition of 6 to give a valid BCD number. So 4 plus 8, which is 12, which is not a valid BCD number. So we have to perform an addition of 6. So 1 0 0 1 1 0 0 plus 1 0 1 1, which is plus 6. And we get 0 1 0 0 1. This carry, so we have to add 3 zeros. So this gives 1 in BCD and this gives 2. In this way, we perform the BCD addition. Next, for the circuit shown, the clock frequency is F0 and the duty cycle is 25% for the signal at the Q output of the flip-flop. Then, the given circuit is this. This is a 2-bit counter clock, and this is a JK flip-flop. And the LSB is applied here. We have an MSB because it's a 2-bit counter, and the Q. This is a flip-flop. If you see this clock signal, which is given to be 25% duty cycle, then it is like 1 2 3. Okay, this is the clock. Then next, it MSB, it will be varying at the pause edge of the clock. So it will be 0 0 1 1 0 0. If you have another clock edge, it will be 001100. And next the LSB. It will be 0101. So 010101. So it's 010101. Next is the Q plus. What will be the value of Q plus when this is value for J and K? So considering this as the J and K, if J and K are 1, 1, it will toggle. So it is in 0, it toggles. 0 remains in the same state. Then again toggles. So it's again here it will toggle. So you can see that this duration is 4 times the time duration and this is 2 times the time duration. So the F0 is F0 by 4 and it is 50% duty cycle. Okay. The next question. In the latch circuit shown, the NAND gate has non-zero but unequal propagation delay. The present input condition is P equal to Q equal to 0. If the input condition is changed simultaneously to P equal to Q equal to 1, the output X and Y will be. And this is the given circuit. X, Y. So X changes first and then Y changes if propagation delay of 1 is less than propagation delay of 2. So if the first output when P is equal to 1 and Y is equal to 0, then X is 1. Next, this Q is 1 changed to 1 and this is 1. So 1, 1 gives 0. Then next, third, P is 1 and Y is 0. This is giving 1. So it is X is equal to 1, Y is equal to 0. Or the other way around, it could have been X is equal to 0, Y equal to 1. Then TPD 1 is greater than TPD. Okay. The next question. Consider the 4-bit D to A converter, digital to analog converter, the analog voltage value corresponding to the digital signal, and from this we get the step size. The step size is 0.0625 and the digital, this is equivalent to 15. So what is the analog voltage? Analog value in volts is 0.60625 into 15 into, yeah, we are multiplying the step size. It's 0.9375. Next question. With respect to ADC, the number of comparators in the 4-bit flash ADC, it is 2 to the power n minus 1, which is 15 comparators are required. So, the next question, the modulus of the counter. So, this and this are 1, then the clear bit will be 1. Oh, sorry, this will be 0 because it's a NAND gate and it will clear the flip flop. So, it will count from 0 to 0110, which is 6. So, second, 0 to 6, which is mod 7. So the value of n is 7. So the next question, in DRAM, periodic refreshing is actually required. Okay, it's actually required, so it's not correct. Information is stored in the capacitor. Yes, information is not stored in the latch, and we can't perform both read and write simultaneously, so it's option B. Okay. Next question. A 16 KB is this much of memory array is designed as square with respect to ratio of 1. Okay, so square memory and the number of address lines required are. So if you see what is the log to 16 kb, it is 4 plus 10. 10 for kb, 4 for 16. It is 14. And this you can see this 2 to the power 4 is 16384 units. Okay, then it's a square arrangement. We have already seen b by 2 is required here, b by 2 is required here. So we have 14 by 2 here and 14 by 2 here. So the required is 7. And the next question. Consider the multiplexer based logic shown here with what is the Boolean logic it is implementing. If this is the question given to us. W. Select lines are S1, S2. So what is the expression? This place after the first multiplexer S1 complement W plus S1 W complement into S2 complement coming to this plus the same term S1 complement plus S1 W complement whole complement S2. Okay, so this is with respect to the multiplexer based question. And next, when the output Y is a circuit below is 1, it implies that the data has the last question. If this is the given question circuit to us, this is connected to, if this is the circuit, then this Y to be 1 with respect to clock, you know D, the output, which is consider Qn complement will be when we apply positive edge clock, it is 0. The output will be 0, 1. When we apply clock edge, if 1, it will be 1, 0. This is the functionality of a D flip flop. Now with this, what is Yn actually? It is Q. If I take this as Q1, 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 Q2. So it is Q1. I will take this as plus for the next state. So Q1 plus Q2. So this will be Q1, which is the okay. It will be with respect to D2. If this is D2. If this is D2, then this is D2. So what is the expression for D2? It is Q1 previous input. What is this one? It is D1. And what is Q1 which is connecting here? This input which is D1 complement. So this one is the Next step. So the D1 is 0 and D1 plus is 1. So it is the data changes from 0 to 1. This 0 is complement, so 1. And this is changes to 1, so it is 1. Okay. So this is the question based on the flip-flops. Okay. So any doubts? Thank you so much. I'm ending the meeting. Thank you so much.